by investigating other properties of these coefficients G. You remember this coefficient G inherit the properties of the elastic matrix. And the elastic matrix, as you remember, is symmetric because it is made of second derivatives, so it is irrelevant in which order we calculate the second derivatives. That reflects into the property that the upper indices of G can be exchanged with the lower indices of G. You can see in the first line on the left that G up MW low NU is equal to G up NW low MU. Okay, so we can exchange the indices of the cell because the elastic matrix element depend only on the relative distances between two cells, between the two cells involved or that appear in the coefficient. So if we exchange the indices of the two cells, nothing changes because the distance is the same. So the first property is the one on the left. Then another property comes from the possibility of selecting arbitrarily the origin. So if we shift the origin to any cell, nothing changes, okay? Because as I said 1 minute ago, the elements of the elastic matrix depend only on the relative distances, not on the position of the origin, okay? So we can replace, if we need it, the index of the cell with a 0, one of them. For instance, index M, okay? So we obtain the relation in the middle of the first line that derives from the translational invariance of the lattice. And the third invariance is the invariance upon reflection. If we put the origin in the middle, the central point of the lattice, okay, and then we swap the positive and the negative side of each axis, nothing changes because the forces, of course, the forces that are present between atoms cannot depend on the orientation of the coordinate axis. So we have another property of invariance that these coefficients do not change if we replace the translational vector of the cell number n with the translational vector minus ln. Okay. These are pure formal properties, okay? They are not simplifications, they are just properties of the lattice, okay? But another simplification that we can introduce is still related to the use of a long wavelength. And we anticipated that before, saying that the displacement of all atoms belonging to the same cell are equal. The displacement of the atoms of one cell with respect to the atoms of another cell are not equal, of course, otherwise the total lattice would shift rigidly, okay? So they cannot be exactly equal, but they are similar. So we may assume that the displacement in any coordinate direction of the atoms of the cell indicated by Ln, that is the translational vector Ln of the lattice, differs not that much from the displacement of the cell near the origin. If that is true, we can expand, we can calculate the displacement of the cell number n using a second order expansion of the displacement of the cell in the origin. So we can approximate psi of Ln, as you can see in the formula at the bottom of the page. It is a second order expansion of psi along all directions, so in 3 dimensions, okay? It is made of a zero order term plus a first order term plus a second order term, okay? Why is it useful to do so? Because after performing this expansion, then we have to replace the expression into the sum that is visible here in this page, okay? We expand psi to second order, then we replace it in this sum, and we shall see that some terms, because of the sum, will cancel each other, okay? So in this way, we introduce another simplification. So we take this expansion and put it into the relation that expresses the dynamics of the cell, okay? So again, we have the total mass of the cell times the second derivative of the displacement is equal to minus. Then we have the sum of these coefficients, and then in the square brackets, we see the second order expansion. Since the second order expansion was too long, the first order term is replaced with dots, and also the second order term is replaced with dots, okay? The issue is that although individually the zero order term is non-zero, and the first order term also is non-zero, when we perform the sum, then the sums of the first order terms are equal to 0, and separately, the sums over the first order terms also are equal to 0. So eventually, because of the summing operation, inside the square brackets, only the second order term will survive eventually, okay? So why are the zero order and the first order term after summation equal to 0? We just do it, okay? We do it. So we have to sum the zero order term over the index n of the cell and the index w of the coordinate axis. We swap the two summations, okay? So we put in parentheses the sum over n first, and then we leave out the displacement that has no dependence on n, because it is that around the origin. And of course, we leave out the other summation, okay? So we are summing up all terms in a single row of the elastic matrix, essentially, in this parenthesis, okay? You may remember when on Friday, we discussed the linear monatomic chain. We found by a simple reasoning that the sum over the index of a single line of the elements is equal to 0, okay? And that depends to the fact that when we perform this sum, we must find 0 because the potential energy of the lattice cannot change by a rigid or because of a rigid translation of the lattice, okay? But this argument also applies here, that is the general case, okay? We easily calculated this property using the monatomic linear chain because it was so easy, because we just had three coefficients, okay? The central one and the two lateral ones, okay? Here, we simply replicate the reasoning. That is, the single line of the elastic matrix has the property that the sum of its element is equal to 0 because of the invariance of the potential energy of the lattice upon translation, rigid translation, okay? So this explains why the zero order term here is 0 after summation. Then we have to repeat the analysis for the first order term. So we now write down the first order term. We have the first derivative here, L and I. N is the index cell, I is the coordinate index. And then again, we take out all the quantities that do not depend on index n. So we leave internally the sum of the elements of the elastic matrix G times the components of the translational vectors L and I, okay? As we noticed before, we can place the origin wherever we like, okay? So we select the cell of index M as the origin, okay? And then, since we have the periodicity of the crystal, we place the origin in the center of the crystal. So this sum eventually will have M equal to 0 here. And M equal to 0 will indicate the cell that is in the center of the crystal. It follows that 1/2 of the vectors in this sum, since the sum is carried out over the total, all cells of the crystal, 1/2 of this vector will be on the right of the origin, so they will be positive. And the other half of these elements, L and I, will be on the left of the origin, so they will be negative. But on the other hand, you remember G is invariant upon reflection. Okay, so G is invariant, as you can see here. And we have a sum in which 1/2 of the element is positive and the other half is equal but negative. So we expect that this sum will be 0. Actually, each term here is made of pieces that add up to 0. Okay, so thanks to this, we can also eventually conclude that the first order term is 0 and only the second order term is left in the equation of the dynamics. So the simplified form of the equation of the dynamics is now this one, okay? At this point, we drop the index of the cell. Why? Because since the behavior of one cell differs very little from the behavior, the displacement of the neighboring cell, we can think of the material, instead of being described by a discrete set of vectors, that is L, we describe it by continuous coordinate. Okay, so we eliminate the indices like M, that is a counter of the cell, and we replace it with a dependence on the position coordinate R that is continuous. So psi here and also at the right hand side will not depend on M anymore, but it will depend on R. Okay. Also, we neglect this suffix 0 because you remember in the expansion we expanded around the origin, but we do not expect that this second derivative will change very much from one position to another, so we do not consider anymore the suffix 0. And finally, we shall change a little bit the appearance of the equation by introducing the density of the material. Okay, for the moment we have considered only the mass of the single cell, that is capital M. Now we consider the density of the material. Of course, the density of the material is equal to the total mass of the crystal divided by the volume. The total mass of the crystal is equal to the mass of the individual cell times the total number of cells. So the total mass is Nc times M. If we divide it by the volume, we obtain the density. The volume is omega. We obtain the density of the material rho. Then we remember that omega over Nc is the total volume of the crystal divided by the total number of cells of the crystal. So omega over Nc is the volume of the individual cell of the lattice. And we already met this concept. We call it tau L, is the volume of the elementary cell of the direct lattice. Okay, so we replace omega over Nc with tau L. One may argue that since there are vibrations that propagate inside the crystal is locally deformed from one position to another and from some time to another time. Okay, so the density is not in principle a constant, okay, but the variations of the density due to these vibrations are small. So we consider the density calculated with when no displacements are present in the material, where there are no vibrations, okay. At this point, we divide both sides of this dynamic equation by the volume tau L of the elementary cell of the direct lattice. So the ratio of the mass divided by tau L, as we anticipated, provides the density, and of course we have to divide by the same quantity also the right hand side. Okay, so then we have a quantity that is, you can see it here, it is, we take the minus, we take these coefficients, these components of the lattice translational vectors, then we have divided by tau, we also collect the 1/2 factor and then we collect the sum over the cell. So after all this collectioning, we have a quantity that is -1 over 2 times tau L times the sum over the cells of G. G does not depend anymore on M, you remember, because we have introduced a dependence on the position, okay? And then we have L and I, L and J, okay? How many indices are there in this definition? Well, M has disappeared because we have introduced the dependency on the position vector R, okay? And this dependency is not here, okay? This dependency is inside this psi in the displacement, okay? Then, so M is not here anymore. Then we sum over the other index N of the cell, so we saturate this index, okay? So what is left, and we saturate also this N and this N. What is left are 4 indices that are U and W, that are collected below here, I and J. So we have 4 indices, and all these indices belong to the coordinate axis. So all these indices, U, W, I, and J, go from 1 to 3, okay? So this quantity, capital phi, that depends on independently on 4 indices, is a tensor of the 4th order or 4th rank. And this tensor is called the elastic tensor, okay? So the more compact expression after these definitions, this more compact expression of the relation of the dynamics is here the density of the material times the second derivative with respect to time of the displacement, not anymore of a cell. This is the displacement at some position R inside the material, because we have switched from a discrete to a continuous description of the material, okay, is equal to a triple sum. It is triple because we sum over W, I, and J of this elastic tensor times the second derivative of the displacement with respect to any 2 coordinates, okay? So this is the compact form of the equation. This form is still very complicated because the elastic tensor has 4 indices that independently vary from 1 to 3, so there are 81 components of the elastic tensor, so it is a rather heavy object to deal with, okay? But you should not be worried about this, because we can see immediately by some reasoning that this elastic tensor can be greatly simplified, okay? So for the moment, observing that there are 81 components, we arrange this tensor as a 9 by 9 matrix, okay? And for instance, we assume that the rows correspond to the 9 possible combination of indices U and W, and the columns correspond to the 9 combination of indices I and J, okay? Now we can immediately start the simplification of this elastic tensor, and we shall see that the simplification is very strong at the end. Because immediately we observe that if we swap L and I with L and J, nothing changes. So obviously, this tensor is invariant under exchange of the 2 indices I and J. But at the same time, it is also invariant upon exchange of the indices U and W, because you remember that G is symmetric with respect to the upper indices and lower indices. So we start swapping the indices and eliminate all the terms of the elastic tensor that are not independent from the other, okay? So let's start with the two indices I and J, okay? If the elements of the tensor do not change after swapping column I with column J, this means that column of indices 2, 1 is identical to column of indices 1, 2. And similarly, column of indices 3, 1 is identical to column of indices 1, 3. And finally, column of indices 3, 2 is identical to column of indices 2, 3. So there are three columns that are useless because they are a replica of other columns. Okay, so we can eliminate three columns. And considering that each column has a length of 9, we eliminate 27 elements. Okay, so we are left with 54. Okay, and since we have eliminated three columns, now the row are not anymore 9 element long. Okay, the column have reduced their length to 6 because we have eliminated three columns. Okay, so we have 54. Now we proceed. We observe that G has the same type of symmetry as the original entries of the elastic coefficient. So the element of this tensor are also invariant upon exchange of U with W. Okay, so again, we repeat the analysis now using the rows. So we have rows of indices 2, 1 is equal to row of indices 1, 2. 3, 1 with 1, 3, 3, 2 with 2, 3. So we can eliminate rows of indices 2, 1, 3, 1, and 3, 2. So we eliminate 3 rows, but now the length of the rows is 6. So we are eliminating 18 terms, 18 entries, and we are left with 36. Okay, so we can rearrange the matrix into a 6 by 6 matrix. Okay, but again, observing the symmetries, we can immediately understand that this matrix is symmetric. Okay, and when a matrix is symmetric, the independent entries are those on the diagonal and 1/2 of the entries that are not over the diagonal. Okay, so in a 6 by 6 matrix, the terms of the diagonal are 6 and the non-diagonal terms are 30. But 1/2 of the 30 non-diagonal elements is identical due to symmetry to those of the other half of the non-diagonal terms. So the independent non-diagonal terms are 15. And then we have the diagonal elements that add up. Okay, so actually we eliminate 15 out of the original 36 elements. That is, we have only 21 independent elements. So this reduction from the original large number of entries that you remember was 81 to 21 has been done only thanks to the original symmetries of the elastic matrix. So no other property of the lattice has been used to reach this level of simplification. So we can always reduce the for all the elastic tensor to 21 independent elements. Okay, so there is a figure that shows the procedure again here. Let me reduce it a little bit. Okay. Okay, so you have the original 9 by 9 matrix. So on the upper edge, you see the indices of the columns that are related to I and J, and on the left edge, you can see the indices of the rows that are related to U and W. Okay, so when we start from the global 81 element matrix, as you remember, we eliminate first columns 2, 1, 3, 1, and 3, 2. So we eliminate the elements that are light gray, okay? And there are 3 columns of length 9. So we eliminate 27 light gray elements, and we are left with 54. Then we eliminate, just in the same way, rows 2, 1, 3, 1, and 3, 2. But at this point, since the light gray elements were already eliminated before, we eliminate only 6 elements for these 3 rows. Okay, so they are a little bit darker, gray darker elements. 6 from this one, 6 from here, and 6 from here. So we eliminate 18 and we are left with 36. At this point, we have the elements in the diagonal. You can see them here, the white ones, these 3, this one, and this one. Then we have the non-diagonal elements, this one, this group here, this one, and all this remaining part of the column. Okay, and then we have the corresponding elements on the other side of the diagonal. But due to symmetry, we can eliminate the 15 elements that are on the lower half of the matrix, and they are the still darker gray elements. So these 3 ones, these 6, this one, and this part of the row. Okay, so we are left with 21. We can continue by introducing other simplifications, and these simplifications are due to the fact that the forces that act from one atom to the other are of the central type. Okay, essentially, the forces are of the electrostatic type, so they are central. Okay, they depend, the force between 2 atoms depends only on the axis that connects the centers of the 2 atoms. Okay, so this is another type of symmetry that we can exploit to further reduce the number of independent terms, and one can demonstrate that in the case of central forces, all indices are interchangeable. So any permutation of the 4 indices will leave the element of the tensor unchanged. Okay, On the other hand, we have already exploited many permutations so far, so there are not so many to be exploited, but there are some, because we have to investigate how many different terms of the tensor still exist in the matrix, in which the indices are a permutation of each other. And there are 6 possibilities. For instance, element here with upper indices 1, 1 and lower indices 2, 2 is non-zero, but also this element with upper indices 1, 2 and lower indices 1, 2 is non-zero. And you can see that 1, 1, 2, 2 and 1, 2, 1, 2 are a permutation of each other. So these two terms are equal. Okay? There is a total of 6 equalities connected to this type of permutations. Okay? So we have the possibility to further decrease the number of independent entries of the tensor by 6. Okay, so we have 6 terms that we can eliminate, and then we are left with 15. Okay, so this completes the description in general. Okay, we have come to this point without specifying what type of materials we are dealing with. Okay, we don't know whether it is silicon or germanium or some other type of crystal. Okay, but if we then specify the type of material, we can still simplify the tensor. And silicon is a very good material because you remember silicon is of the cubic type. Okay, so in silicon, you remember the length of the 3 characteristic vectors of the direct lattice is equal, and these characteristic vectors are normal to each other. Okay, so this introduces another simplification that is enormous, because in a cubic crystal, the number of independent entries of the tensor, that in the general case is 15, as you have seen now, reduces to just 3. There are only 3 independent terms of the elastic tensor, and we can write them in this form. Actually, further considerations show that the equality are of this type. So eventually, the 6 by 6 elastic tensor becomes a tensor in which we have a 3 by 3 block whose diagonal elements are equal to each other. Call them phi A. And the non-diagonal element are also equal to each other but different from the diagonal ones, so we call them phi C. Then the lower block is purely diagonal, and its elements are equal to each other on the diagonal, and we call them phi B, but phi B is different from phi A and phi C. Okay, so eventually, for a cubic crystal, we end up with this form of the tensor in which only 3 elements are different, are non-zero and different from each other. Basing on this analysis, we now stop because we are almost near the end. We can introduce concepts that are typical of the theory of elasticity. and they are used very much by mechanical engineers and civil engineers, okay? And this relation, as we shall see in the second hour, are greatly simplified thanks to the simple form of the tensor and of the symmetry properties that we have investigated. So for the moment we stop and we shall restart in about 10 minutes. Okay, so we resume the discussion. Now that we have understood that the indices of the elastic tensor are all interchangeable, we can exploit this property by simplify, thanks to this, the expression of the dynamic relation. So we take again the relation of the dynamics of the displacements, density of the material times the acceleration along one of the three directions is equal to the triple sum of the tensor times the second derivative of the displacement. Okay. We start interchanging the indices. We do it on phi first. You see that when we go from the first line to the second line, here we have exchanged W and I, okay, with respect to this, because phi is invariant. Then we again exchange W and I, but we do it all over the indices, okay? So we do it on phi so that we recover back the original expression, but we do it also on the derivatives, okay? This is perfectly legitimate because phi is invariant and we have a summation over all indices, okay? Then we extract the derivative with respect to W, and we split the other derivative into two parts. We have 1/2 the first part plus 1/2 the same thing, but in the second summand here, we exploit again the invariance and we swap the two indices. So ij become ji, and we have to do it also in the derivative, okay? Next, we observe that in this form of phi, we can put back the two upper indices in the original position. So we extract phi ij uw and the term 1/2. And eventually, we have defined a symmetric tensor that is the quantity in parentheses, okay? This tensor is made of the derivative of the ith component of the displacement with respect to the jth component of the coordinate plus the opposite, the derivative of the jth component of displacement with respect to the ith component of the coordinate, okay? This tensor, including the 1/2 factor, is called the strain tensor. Okay, this is the strain tensor. We shall find it again in the applications very soon. Okay, so that after rearranging the expression of the dynamics and introducing the strain tensor, we have that the acceleration times the density is equal to the sum over W of the derivatives of this other quantity here. Okay. Observe two things. One thing is that the strain tensor is symmetric because it is invariant after exchange of the two indices I and J, and also that the strain tensor is dimensionless because the denominators are coordinates, but the numerators are displacement, so length over length. Okay, so this tensor is a pure number, but this means also that the units of phi divided by a length must be equal to the units of the left-hand side. Okay, so what are the units of the left-hand side? Well, the density is a mass over a volume. Okay, and psi dot dot is a length over a time square, so it is an acceleration. Okay, so globally, the left-hand side is an acceleration times a mass that makes a force divided by a volume. So the left-hand side is a force per unit volume. So that means that phi over a length is also a force per unit volume. Phi over a length, which means that phi by itself is a force over an area. So phi, the fourth rank tensor, is a force per unit area, and this quantity is also called, in this context, is called a stress. Okay? Conclusion. All the sum of elements like phi times the strain tensor, remember the strain tensor has no dimensions, so this sum has the same units as phi. And of course, we sum up over the two indices that are I and j, so globally, this quantity eventually depends only on u and w. It is a stress, that is a force per unit area, and it is defined as the stress tensor. Okay? So, in conclusion, when we start from the microscopic situation in which we describe the dynamics of the crystal atom by atom, so to speak, okay? After some simplifications, essentially due to the consideration only of the long wavelength relations, okay? That is, we are considering the acoustic modes at long wavelengths near the origin of the angular frequency, okay? The dynamics of the displacements simplifies to this relation, that is that the acceleration times the density, the acceleration of the individual component of the displacement, is equal, this is essentially the divergence of the stress tensor. Okay? You see that essentially this is a generalization to 3 dimensions and to the anisotropic case of a very, very old law that is, as you remember, Hooke's law of elasticity. Okay? If you remember, the Hooke law was the first law that was stated about elasticity, and simply states that if you pull a piece of material, you obtain an elongation that is proportional to the applied force. Okay, this is stated in better terms here, saying that the the strain and stress tensors, okay, have this relation between each other, and the application of this law to simple cases shows that indeed we can recover Hooke's law from this relation. Okay, the first the year in which this law was mentioned is, as you can see here, 1676. Okay, and we shall come back to it very soon. Okay, so we now apply these relations to very simple situations in which we take a prismatic block of material in which the three sides are A1, A2, and A3. It is shown in a figure that will here, okay? So we consider, if you look at the lower left part of the figure, a prismatic block of material in which one vertex is in the origin. The length of the three sides are A1, A2, and A3, and the sides are aligned with the coordinate axis, okay? And the purpose is to understand what happens if this block of material is subjected to external forces, okay? In general, this block of material is not alone, but it belongs to a larger body. Okay, so you may imagine that this block of material belongs to a much larger body that is, as a whole, subjected to external forces that produce deformations. Okay, so since all remaining parts of the external body are subjected to deformations, this little block that we are seeing in this figure will also move because it is attached to other parts that are moving because of the deformation, okay? So we expect that there will be a rigid shift of this block. There will also be a rotation of this block due to the deformation of the rest of the structure to which this block is attached. And finally, there will be a deformation of the little block itself, okay? The only aspect in which we are interested is the deformation of the block itself, okay? So we do not consider the larger motion made of a translation and of a rotation due to the fact that this little block is attached to a larger structure, okay? So we, at some point, to eliminate these other aspects of translation and rotation, we shall consider a local reference that is connected to this block, like the axis x1, x2, and x3 that you see in the figure, and we shall consider only the deformations of this little block with respect to the undeformed state of the block itself, okay? Okay. This is what I just said about the local reference. And then we make another assumption. we make the assumption that the internal points of the little block that we are considering, due to the deformation, are displaced with respect to the undeformed condition. But we also assume that the displacement is small. So we take any point inside the block, and this point has coordinates x1, x2, x3. Of course, this point will be subjected to a deformation in all directions. So we consider the deformation with displacement psi I in the direction I. And we assume that it is small, okay? So we expand it to first order. When we expand it to first order, the zero order is zero because it is related to the undeformed situation in which there is no displacement, okay? So we calculate the first order expansion, as you can see in the figure. And as you remember, we have placed the origin in one of the vertices of the block. Okay, so we are referencing the coordinates x1, x2, x3 to the origin that is 0, of course, of the same block. Okay, and these coordinates and these derivatives are also calculated in the origin. Okay, now you can see that all these derivatives, if we move all indices from 1 to 3, form a tensor because we have one index attached to psi that goes from 1 to 3 and another index attached to the coordinate that also goes from 1 to 3. So this quantity, this derivative d psi I over dxj is a rank 2 or order 2 tensor of order of side 3, it's 3 by 3, okay, that we can express as a sum of a symmetric and an anti-symmetric tensor. We simply split the derivative of psi with respect to j as 1/2 itself plus 1/2 itself, and then we add and subtract the 1/2 of the derivative of psi j over xi, okay? Obviously, the first part is a symmetric tensor, and you can recognize immediately that this is the strain tensor, okay? And this other tensor is anti-symmetric. That means that if you swap the indices, this second tensor changes its sign, okay? Now, the first part was already defined. You remember, it is the strain tensor epsilon. The anti-symmetric part, we call it theta. Okay, theta is the anti-symmetric tensor with this form. And you see immediately that this tensor has only 3 non-vanishing entries because the entries in which I is equal to j are 0. Okay, obviously you see from the definition. And the entries of indices 2, 1, 3, 2, and 1, 3 are the negative of the entries of indices 1, 2, 2, 3, and 3, 1. So this tensor is a tensor with 0 diagonal and anti-symmetric, okay? So if we use this definition and express all these derivatives using the tensors, okay, we find relations like this, okay? Now, the components psi1, 2, and 3 are those of the displacement. The displacement is written in terms of the coordinates of the point that is being displaced using the strain tensor and the other tensor. Okay. Now, the other tensor can be written in short form as a vector theta of components theta 1, theta 2, and theta 3, vector product the coordinates. You can see immediately that these differences are exactly the components of this vector product, okay? And this is related to a rotation, okay? So globally, these expressions show that a displacement can be written as the combination of a rotation here, that is a rigid rotation, and a deformation described by the strain tensor, okay? We already anticipated that the rotation can be disposed of because this rotation has no effect on the potential energy. There is no difference in the relative positions of 2 points of the little block due to the rotation in itself. The only change of the internal distances is due to the deformation, and the deformation is described by the strain tensor, okay? So from now on, we assume that we are considering only a local reference that is rigidly connected to the block, okay? So we shall not have any rotation anymore, but only the deformation. Now let's take some special example of deformation. Assume, for instance, as a first possible example, that we want to consider a deformation that takes place only along the third axis. So we assume that the deformation is 0 along axis number 1 and axis number 2. If you look at the figure, we assume that the forces applied to the little block are such that we have a deformation only in the vertical direction and no deformation of along x1 and along x2. And also that we want to calculate how the upper face deforms, okay? But the upper face has a coordinate that is equal to A3, okay? Because if you go here in these expressions, if you want to analyze how the upper face deforms, you should replace the generic position x3 with A3, okay? Then consider that all the rest of this is 0. You find that psi1 and psi2 are 0 as we anticipated because there are no deformation along the first and second axis, and that at each position of the upper face, so for any x1, x2 of the upper plane, the deformation of this upper plane is given by E33A3. Okay, so we have only the deformation along this direction, number 3. Okay, it's like somebody is pulling the upper face upwards. Okay, the deformation will be epsilon 33 times A3, okay? There will be no rotation of the upper face and no rotation also of the other face. So the upper face will still be parallel to the original plane, okay? We can conclude that the entry epsilon 33 of the strain tensor multiplied by A3 gives the elongation by which the little block deforms due to the action of a force that is pulling in the upward direction, okay? If the product epsilon 33 times A3 is the deformation, A33 by itself, that is the deformation divided by A3, is the relative deformation in the direction normal to the face. So, of course, we can repeat the reasoning for a deformation to the left, that is along x1, or a deformation to the right, that is along x2, okay? So the diagonal elements of the strain tensor are the relative shift with respect to the undeformed case along the corresponding direction. These shifts are also called, sorry, not the shift, the diagonal elements of the strain tensor are called extensions, okay? Now we take a second example. Consider that all the entries of the tensor are zero with the exception of epsilon 2, 3, that is a non-diagonal element. And again, we look at what happens on a face. For instance, we consider the condition x2 equal to a2 and x3 equal to 0, okay? We see it in the calculation here because we have the formula. We find that the deformation in the direction number 3 is equal to the product epsilon 2, 3, that is the only non-zero component of the strain tensor, times a2. But it is much more easily understood in the figure if we start from the undeformed situation and we want to understand what happens of this line that is originally in this position, okay, and the vertices of this line are A1, 0, A3, and respectively 0, 0, and A3, okay. This line will deform to the right, will shift, sorry, to the right by the amount calculated before, epsilon 2, 3 times A3, okay. This is a different type of a deformation with respect to the previous one, okay? Because in the previous one, all the planes will go up symmetrically, okay? Because we are pulling normal to the face. In this case, the type of deformation is due to the fact that we have a force that is horizontal on the upper face and shifts the upper face to the right, whereas the lower face stays where it is originally, okay? So this type of deformation is different from the other. And we can calculate also the angle by which the plane, this plane here, the plane that is originally on the x1, x3 axis, okay, this plane rotates. The angle is here. And of course, if you take the product of this displacement that is given by epsilon 23 times A3, and then you divide it by A3, so you take the relative displacement, you find that it is equal to epsilon 23, and it is also the tangent of this angle, because it is the ratio between epsilon 23 times A3 and A3 itself, okay? But this angle is very small. So the tangent is practically equal to the angle itself measured in radians, okay? So this explains also what the meaning is of the non-diagonal elements of the strain tensor, okay? They provide the rotation angles, okay, that appear under this type of force applied to the material. There is also a name to this type of force. It is written here. This type of strain is called shearing strain or detusion, okay? So the one that is associated to a relative shift of the opposite faces of the material parallel one to the other, okay? Obviously, we may also have combinations of these types of deformations, and all these combinations are linear because they are so small that they combine with each other linearly. So probably there is a figure in which we have two of them here. Now this is again a shear, but in this case the shear is due to a force that is applied, a vertical force applied to the right face that tends to rotate the element with respect to the left face, okay? So in this case, the angle is this angle here, and it will be given by E epsilon 23. When you have two of these type of deformations, you have the combination of them, and the combination is taken linear, so the higher order terms are neglected because the deformations are small. Now, we want to connect the theory to the macroscopic theory of elasticity. So far, as you remember, we have started from a microscopic description, and this microscopic description of the dynamics of the single atoms, introducing some approximation, has brought us to the equation, to an equation that is the equation of elasticity. Can we derive the same equation from macroscopic principles? Well, yes. The issue is, do we find the same thing? And the answer is yes, we find the same thing. If we start from microscopic or macroscopic considerations, eventually we find the same type of equation. So what do we do if we start with a finite block of material? As you remember, this block of material is to be considered as internal to a much larger structure. Okay, so it is an internal small piece of a body that could be a bridge or an engine or a dam or whatever. Okay, so where do the forces that are applied to the sides of the small block come from? The forces come from the rest of the structure. Okay, so you must imagine that you are zooming into the structure, you are extracting a little block, and you want to consider the forces that are applied on the faces of this little block. In order to do so, what you do is you eliminate the remaining part of the structure, you leave the little block alone, and you replace the part of the structure that you have eliminated with the equivalent forces that the eliminated part was exerting on the little block. Okay? And what are these little forces? Well, of course, you remember that any system of forces in the three-dimensional space can eventually be reduced to two things, one force and one torque. Okay, so we have one force and one torque acting on each face of the elementary block that you are considering. Okay. Obviously, the force and the torque will depend on the area of each face and on the orientation of each face. Okay. But actually, when we consider a little block, we typically consider not the force or the torque, but we consider the force per unit area, that is the stress, and the torque per unit area, okay? And it happens that, well, the area does not go exactly to zero, okay? But it is very little eventually. So it is found that the torque per unit area is smaller, is an infinitesimal of a higher order if you go to zero than the force per unit area. Okay, so eventually this is reasonable because the torque is proportional to a length. Okay, so when the lengths go to zero, it also goes to zero. The force is not. So the force over the area stays finite, whereas the torque over the area goes to zero. Okay? So thanks to this, we may consider only the force per unit area, the area that is the tension or stress. Okay? And we do not consider anymore the torque. Okay? Now I have to change the slides. So I will try to put on the screen other slides because they have information that is connected to this, but better visible. So let me try to Okay, let's try to see whether you should see a slide called Advanced Solid Phase Sensors, Susanna Reggiani. And this belongs to a set of slides that I will upload later in the website. This is a little list of typical applications of Can you put the microphone off, please? Okay, I've blocked the microphone because I had some sounds in the earphones. Let's go back to the okay, these are the possible applications of solid-state mechanical microsensors. We may measure pressure, stress, acceleration, deceleration, displacement, flow rate, force, torque, position, and angle, many things. Of course, these measurements may interest widely different amplitudes of the signal. For instance, in this slide, you see what are the typical accelerations that could possibly be detected by accelerometers. Okay, we have the large ones that are those associated to the airbags in car. Frontal airbags may go in the range of 50 G. G is the gravitational acceleration, of course. Lateral airbags, even larger. Suspensions and ABS, the anti-lock braking system, much smaller than that. This slide illustrates the units. Okay, the units of pressure are many. So one typical unit is the Pascal. That is the unit of pressure in the international system. Of course, we have the kilopascal, that is 1000 Pascal. Another possible unit is the unit indicated as 1 force kilogram per square meter. Okay, so it is, of course, 9.8 Pascal, because we have the factor of the gravitational accelerometer in between. The British units are the pound force per square inch, PSI. remember that 1 inch is 25.4 millimeters, and a pound is such that to make 1 kilogram you need about 2.2 pounds. So 1 psi is about 6.89,000 Pascal. One other unit of pressure that is, of course, used for measuring the atmospheric pressure is the mercury millimeter. So 1 mercury millimeter is equivalent to 1 torr, and it corresponds to 133 pascals. It is implied that the mercury must be liquid, so that the density of it in the liquid phase is, as shown here, is 13.59 grams per cubic centimeters. This is the density of the liquid mercury. The atmosphere, the standard atmosphere at 0 degrees centigrade is equivalent to 760 torr, or about 1 times 10 to the 5th Pascal. By the way, 1 atmosphere is the pressure of the atmosphere, of course, at 0 degrees. That is a column of air whose height is equal to the height of the atmosphere, but it is also equivalent to the pressure exerted by a column of water whose height is 10 meters and 33 centimeters. Okay, so if you go down in water by 10 meters, you have 2 atmospheres on you. One is the water plus the air on top, and 1 bar is 10 to the 5th pascals. Okay, so these are the many units that are used for measuring pressure. Again, there are different ranges for pressure sensors. So generic pressure sensor may go to between 15 and 250 kilopascal. Tire pressure is much less, between 1.8 and 2.5 bar. Blood pressure, it should, I mean, 30 is too little, I mean, and 300 is too much. So regular blood pressure goes between 780, the minimum, and 120, 130, the maximum, okay? The pressure of the atmosphere, of course, depends on the altitude. So 760, as you know very well, is the barometric pressure of the atmosphere at sea level. If you go up 5,000 meters, it goes down to about 400. And if you climb up Mount Everest, it goes down to a little bit more than 200. Now we devote the few minutes left, or just 0 minutes left, to redefining some of the properties that we examined before with the calculation. I will limit myself only to the definition of Hooke's law in the very simple form. If you have a bar of length L0 that is unperturbed and you pull it with an axial force, a force that is oriented along the axis of the bar, if the force is F, the stress is sigma equal to the force over the area of the cross section of the bar, and the strain is the relative variation. So it is the elongation delta L0 normalized to the unperturbed length. Okay, so we have to stop now because it is already 7. We shall continue on this issue tomorrow afternoon. Thank you for the moment.